In section 2.2 of intermediate algebra, we are going to cover something called the algebra of functions. Having introduced the concept of functions in section 1, we are now ready to take a closer look at things that we can do with those functions. For example, when we first introduced numbers, one of the first things we learned how to do was to add, subtract, multiply, and divide numbers. Well, guess what? If we have those operations with numbers, we can also have those operations with functions. We are going to talk about how we add, subtract, multiply, and divide functions. Prior to that, even though, we're going to talk about a little bit more in detail of how we identify the domain and range of a function. In the last section, I talked about how, as we introduce new functions, one of the first questions we always ask is, what is the domain? What is the range of that function? One way that we have already covered to identify the range and domain for a function is to look at its graph, but sometimes that's not always available, or doesn't always give us the complete picture of what's going on. We can't look at the entire plane because we have to draw our boundaries somewhere. We can only plot parts of graphs in most cases. So we need another technique for identifying the domain and the range of the function. So that's what we're going to be doing in section 2.2, the algebra of functions. So to summarize, the essential concepts for this section will be to find the domain for a function, to find the sum of two functions. Actually, we're going to find, I should go ahead and say this, the sum, difference, product, and quotient of two functions. And we're going to use the algebra of functions to combine and determine the resulting domains. Finding a function's domain. If the function f does not model data or verbal conditions, in that case its domain is the largest set of real numbers for which the value of f of x is a real number. Now basically what I'm saying with this statement is, in the event that we're looking at just the formula for the function, as you see two formulas down here, and not within the context of a particular problem where, for example, we may be modeling something in the real world and we're talking about dollar values, so we're limited to actual discrete values of the dollar. Or if we're talking about time, we wouldn't ever talk about negative time in those examples. Excluding those cases where context makes a difference, if all we have is the function, what we're going to mean by the domain is that it is the largest set of real numbers for which we get an output that's a real number. Basically, for us, that means two things. We're going to exclude from the function's domain the numbers that cause division by zero. Anything that would cause a division by zero would be left out of the real numbers. So we'd say all real numbers except those. And we're also going to exclude from the function's domain any real number that results in the square root of a negative number. Remember, because we cannot take the square root of a negative number, as we covered back in chapter 1. So, in this particular example, we're asked to find the domain of the function f of x is equal to negative 4x squared minus 2x plus 7. Now, to check the domain, we're going to check these two conditions right here. Is it possible that we would divide by 0 by plugging in any number we wanted for x? Are there any numbers we could plug in for x into this formula that would result in dividing by 0? And the answer is no, we can't do that in this example. What about square roots? Well, there's no square roots. So according to this, I should not exclude any real numbers. That means that the domain is this set, which is my symbol for all real numbers. The domain of this function here is everything, right? It's domain, it's dominion, if you will. It's kind of a play on that word there, but that means everything that this function has an effect on, we're allowed to plug in any real number at all. Now what about this example here? Now we have fractions with variables in the denominator, which means that it is possible to end up with values that would make this divide by 0. Right? Now, what values make it divide by 0? If you have 2 over x minus 4, clearly a 4 would do it, right? But how do you find it explicitly? What you're actually saying is, I'm going to take the denominators and I'm going to set them equal to 0 and find the values of x that make that true and then exclude those from the domain. So if I solve this equation, add 4 to both sides, I have x equals 4. Solve this by subtracting 5 from both sides, I have x is equal to negative 5. So what does that mean? The domain is going to be the set of all x such that, all real numbers x, such that x is not 4 or negative 5. That's how I would write that domain. Everything except 4 and negative 5. Now let's talk about the algebra of functions. Right? This is where we're going to talk about how we add, subtract, multiply, and divide functions. And really, it's pretty obvious what we're going to do here. If I say, let's find the sum of two functions. So I've given an example up here. We've got f of x is this formula, 3x squared plus or minus 2, and g of x is 4 plus x. So what does the sum function mean? What is the sum of two functions? That means to take f of x plus g of x. That means take the formula for f and add it to the formula for g, and that's what we get. So the new function, which I will call f plus g, now the output, I shouldn't say the output, the result or the answer to the sum of two functions is a new function, right? Add a function to a function, you get a function. So I'm going to write this in function notation. This is the name of the function, f plus g. It is dependent on the variable x. So this is f plus g of x, and I get it by taking f of x plus g of x. In other words, I take 3x squared minus 2 in this example and add 4 plus x. Now if I combine like terms, I will get 3x squared plus x plus 2, right? Because there's just a single x, but minus 2 plus 4 is plus 2. So f plus g as a function of x is given by the formula 3x squared plus x plus 2. The difference, similarly, would just mean to take the difference of the two functions. So I would go through the exact same procedure again. That f minus g as a function of x is f of x, the function, minus g of x, the function. So that's 3x squared minus 2 minus 4 plus x. Now I'm careful to put the parentheses around it this time because I need to distribute the minus sign to each term here. That's just like a minus times this, so there's a distribution rule. There's just a 1 here, so I can actually drop the parentheses. I get 3x squared minus 2 minus 4 minus x. That gives me 3x squared minus x minus 6. So f minus g as a function of x is given by 3x squared minus x minus 6. As you may guess, the product of these two functions means to take f of x times g of x. So if I wanted to find fg as a function of x, I will take f of x and multiply it times g of x. That is, I will take 3x squared minus 2 times 4 plus x. Okay, so that's what I would write as my fg of x. Now we'll talk later on about how we multiply out two binomials or two we'll multiply out this expression. Without giving it a name, we'll just say we're going to multiply out that kind of expression later on. But one other type of example, I want to throw it in and squeeze it in here, that you might see is you might be asked to find fg, but you might also be asked to find fg of negative 3. Now what does that mean to do? Well, that means to take the negative 3 and stick it in to this formula. That is, you're going to take 3 times a negative 3 squared minus 2 and a 4 plus a negative 3. Right? Because fg of a number means plug that number in for x, which you would then simplify. You would have here 3 times 9 minus 2, and 4 plus a negative 3 is 1. So 3 times 9 is 27, minus 2 is 25, times 1 is 25. So that's the output from the product function. Right? The product of these two functions is this formula here, and then that product function of negative 3, the output is 25. Okay? So that's how we would do an example like find fg of negative 3. Find the formula for fg and then plug in negative 3 into it. The quotient function, same deal, right? You're going to have that f divided by g is, I'm going to use this as my fraction bar here, is f of x over g of x. Right? So in our example, f over g of x would be 3x squared minus 2 for f of x over 4 plus x. There it is. That's all you got to do. So if you were asked, just as an example, f over g of 8, you would find 3 times 8 squared minus 2 over 4 plus 8. Right? That's 3 times 64 minus 2 over 12. 3 times 64 is 192. Minus 2 is 190 over 12, which reduces to 95 over 6. Okay? All right, that's how we find the quotient function. Here in this example, we're given a table that shows the total number of births and total number of deaths in the United States from 1995 through 2002. The data can be modeled with the following functions. The number of births modeled by the function b of x is equal to 24,770 times x plus 3,873,266. While the number of deaths can be modeled by a similar function d of x. Okay, 20,205x plus roughly 2.3 million. All right, in each of the functions, x represents the number of years after 1995. So 0 would be 1995, 1 would be 1996, and so forth. Assume the functions apply to only the years shown in the table. Let's answer the following questions. So let us consider now how we would find the domain of b. Okay, the domain is going to be everything that I can plug in for x, right? Now I'm not going to plug in these numbers, even though x represents year. It doesn't represent 1995, but years after 1995. Okay, and we're going to assume that the function only applies to the years shown, which means it doesn't apply anywhere in between 95 and 96. So we wouldn't have 1995 and a half. We just have 1995. So the domain of b is the set of all x such that x is, well, 1995, that would be x equals 0. 96 would be x equals 1. 2 is 97. 3 is 98. 4 is 99. 5 is 2000. 6 is 2001. And 7 is 2002, and that's it. That's the only values for which it applies. Not every number from 0 to 7, so I wouldn't do x between 0 and 7 because we can't plug in decimal numbers. This only is valid for actual year values. And the domain for the function d is still the same as that, right? It's still 0, 1, 2, 3, 4, 5, 6, 7, because it applies to the same years. Now, because the domains are equal, the same domain, we can plug the same numbers in. We're going to consider combining those two functions into one and taking births minus deaths. Okay, b minus d of x. Right? That function, by definition, as we've covered earlier, is b of x minus d of x, which is 24,770 x plus 3,873,266 minus, I'm going to go to the next line, but imagine this is all one line here, 20,205x plus 2,294,970. Okay, so we now simplify the formula by distributing the minus sign to each of these, right, to here and to here. So that means we'd have 24,770x plus 3,873,266 minus 20,205 x minus 2,294,970. Okay, so collect like terms. 24,770 x minus 20,205. Plug that into my calculator. I get 4,565 x plus 3,873,266 minus 2,294,970 gives me 1,578,296. Okay, that's b minus d as a function of x. Now, what does that represent? What does this function here actually mean? Well, that means births minus deaths. If you think about it, that's the population change. That's the net growth in per population, right? Because you have births adding to the population, deaths taking away from the population. So this is your net growth in population each year. So let's find the net growth in population in year 6. That means since 2095, or 1995. So 1995 plus 6 is in 2001. Right? So we're going to be finding the net growth population in 2001. Okay? So I'm going to find this and plug in 6. Right? I've got b minus d of x is the above formula. So if I want to find 6 for x, I'm going to do 4,565, plug in x, plus 1,578,296. Okay, that times 6 gives me 27,390 plus 1,578,296. Add those up, I get 1,605,686. Okay, there was a net growth of 1,605,686 people in 2001. Okay, that's what it means in terms of U.S. population. All right, and that's the end of section 2.2.